Welcome to the Math Record. Today we'll be starting to cover the concept of integrals. This video will cover part 1 of chapter 3 in our calculus class. Okay, let's begin. So what is an integral? Well, basically an integral is like an antiderivative. So what I mean is that if you have the original equation, let's say it's x squared, right? Then if you do the derivative of that, you get 2x. The idea of an integral would be to get from 2x back into x squared. So what this looks like visually is basically we're going to have a graph. So let's take, for example, our 2x, right? So we have 2x. And let's say we put a restriction. Let's say it goes from x is from here to x is here, right? So basically, if you find the area under this graph, this area under this graph would resemble your x squared. So how that will look basically is that if we have, let's say, a point here, let's call this 1, 2, 3, right? And then if we find the area from 0 to 1 and from 0 to 1, and we call that area 1, right? And then we find the area from 0 to 2, right? From 0 to 2, and we call that area 2. And we find the area from 0 to 3, right? And we call that A3, right? And we call this like the first point, our second, this would be our second, and this would be a third. If you kind of graph these points out, you're going to see that they kind of represent a like quadratic equation. And that's because of how integrals work. So the idea of integrals is basically an antiderivative. So instead of going for the original, you go to so the derivative goes from the original to the derivative, and integral goes from the derivative to the original function. So, and additionally, integrals, to find it, basically you just find an area under the graph, which is what is most commonly used for, just basically finding area under the graph. Okay? So, further on with the integral for area is if you kind of do an area under the graph. So let's say we stop it right here. Okay? And we do the area under the graph. This area is called the displacement. So there's two different ways to measure distance. Distance could either be used for displacement or for total distance traveled. So basically what it is that let's say you start at this point and then you move 5, right? And then from that point, you move back 3. So what is the total distance traveled? Well, basically it's just 5 plus 3, right? So you travel 8 distance. The displacement is different. Basically, what the displacement only matters is the only thing that matters in the displacement is the initial position and the final position. So it only matters from here to here. So this is the only distance that matters. So if you go 5 and then you go 3 back, basically you only travel a distance of 2, right? And that's all that matters for displacement. So a total distance is 8, the displacement is 2. So don't misunderstand. So what the when they ask a question about total distance traveled, this is not the total distance traveled. This is the displacement. But displacement could also be a total distance traveled. What this basically accounts for is basically if you have something like negative to positive. So let's say you have something like this, right? And then if you do an area under here, so if you do an area for this, only this part, since all these points are positive, then technically the displacement is equal to the total area. I mean total distance. But if you do the area from like here and here, right? So from this point all the way up to this point, then basically what you have is that you have this area subtracted by this area, because this area is negative, this area is positive. The area is negative if it's below the graph. The area is positive if it's above the graph. So what it basically is that if you have this area subtracted by this area, that's going to be our displacement. So our displacement is not going to be the same thing as our total distance, because our total distance would be the positive version of this area plus this area, right? So you just basically take in the absolute value of each. So because then it makes it both positive. So we can add those areas together. That is going to be our total area. But our displacement is basically this positive minus this, because this is negative. And that's the idea of displacement. So the reason I'm covering displacement is because if we have an original function, like let's say we have y is equal to x squared, right? And if we take the derivative of that, that's 2x, right? Well, if we have y is equal to x squared plus 5, right? So we just add 5 to this y. Well, if we do the derivative of this, we get 2x, and the derivative of 5 is 0, right? So they have the same derivative, but they have had different original functions. And the reason is because the the height that's added to an equation does not change the derivative. It just doesn't. The reason is because let's say we take like a quadratic, for example, right? And then um we take something like right here, okay? So if we take a derivative at this point right here, and when we choose the same point, right here, then basically these two slopes are exactly the same, right? It doesn't matter, because if this point right here is the same point as this point right here, right? So if this point moves up 5 to get to this point, right? Then basically every single other point on this graph has to move up 5. So the definition of slope is change in y divided by change in x. So technically, since all the y's are changing by the same amount, that means the change in y shouldn't technically be the same. So the slope should technically be the same, right? Because if this is going up by 5, then this is going up by 5. So if you have a y value of like 1 and it went up by 5, and the y value of the second one went up to 5, then the change in y would just be y2 plus 5 minus y1 plus 5, which is just y2 minus y1. And the original was just y2 minus y1, which is basically the same thing. And that's why it doesn't matter if you add the 5 there, because it's not going to affect anything. You're just changing the height. You're not going to change the slope at all. So that's why there is a idea about displacement and why I'm covering it, because if we take the derivative, like they both have the same derivative, right? So we take the derivative, and let's say we want to find when what the point is. You want to find the y value when you have x is equal to 5. Then basically, you're gonna have x is equal to 0. You're always gonna start from 0, usually, and then you're gonna have 5 because you want to go up to x equal to 5. And this is y equals to 2x. You have to find the area from 0 to 5, right? So for this example, the base is 5. This is just a triangle, so the base is 5. And the height is basically 10, because this is y is equal to 2x, right? So 5 times 2 is 10. So this is up to 10. So this entire length is 10. So 10 times 5. So divide by 2. So that will equal to 25, right? So our area is 25. So area is equal to 25. So to find the point at x equals to 5 would basically be the area plus the initial point. So what this basically means is that since the area is a displacement, what we need to have is the initial value plus the amount that's displaced, and then gets the final point, right? Because based on the example that I used, right, you went here and then you went here. Well, if you have the initial point plus the displacement, this is your displacement, then you get to this point. Then that's the basic idea of how this works, because it doesn't calculate for total area. Because if you're calculating for total area, then you go from here and then you go from here and then you get this point, right? But what happens is that you go here, and then this is a positive area, right? So it goes also here, so it went over here, which doesn't work. And that's why this area helps us find displacement. But if they're all positive, then it's also equal to total distance. So it could be equal to each other, but not all the time. So based on this, for example, we have area is equal to 25. So thus, So for us to find the point at x is equal to 5 for these equations, the questions usually have to give us an initial point. So it has to give us at least 1 point for the original function. So for, let's say right here, they give us the point 0, 0, right? And then from this equation, they give us the point 0, 5. So what we had to do is that basically you have to have the area plus our initial point. So our initial point is just f of 0, basically. So our f at 0, the 0, f of 0 is 0. So the area is 25 plus our area plus the initial point, which is 0, is equal to 25, right? So x is equal to 5 for this equation, which is true, is 25, which is true because you put in x equal 5, that's y is 25, right? So let's try the same idea, but now with x is equal to y squared plus 5, right? So our area plus our initial point. So our area is 25. Our initial point is 0, 5, right? So when x is equal to 0, you have to add 5. So 25 plus 5 is 30. So the the y value when x is equal to 5 for this equation is 30. Right? Which makes sense because when x is equal to 5, that's 5 squared, which is 25. 25 plus 5 is 30. And that is correct, basically. And that's the idea of having a displacement, like a practical way of using an integral. So let's actually cover a general idea of how integrals work. So how this usually works for integrals is basically you're going to have two notations. There's a s, and then you're going to write your equation. Let's say our equation is 2x plus 5, okay? And then we're going to have some another notation, which is 2x. I mean, dx. This thing tells us, all this tells us is basically just to take the integral. That's basically what it means. That's all it does. This thing tells us is what we take a respect to. So what I mean is basically um a simple way to explain this is that this variable has to be the same thing as this variable. So the reason we put dx is basically the respect to tell us it's respect to x. That's why it's called dx. So what it's basically writing is like, let's say we have y is equal to 2x plus 5, right? You're taking the derivative of y in respect to x, right? And that's why it's called dx. But now if we take b is equal to 2a plus 5, right? We're taking the derivative of b in respect to a. You see how that works? Because we're taking like the respect to whatever our x variable is, like our x-axis variable, right? So what that would be instead of writing dx, we'll be writing dA. It's basically just that simple. It's just telling us what we have to take the respect to. In this form, this integral from 2x plus 5 at dx, if you kind of graph this out, right? Let's write it right here. Okay, not the straightest line, but it will do. So basically, what it does is that this is referred to as an indefinite integral because this equation goes to infinity, right? Because if you go, you could, as x goes to negative infinity and x goes to infinity, right? In both cases, this line will go to infinity, right? Which is true. So that's an indefinite integral. To make an indefinite to a definite, so it does have like a limit amount. So instead of having it go from infinity, what we do is that we kind of domain restrict it. So what we do is that we have like, let's say like only this portion of the graph. And then instead of like finding the, because like if it's an indefinite, you can't find the integral because it goes for infinity, right? Well, basically to find the area of a integral, we just only take part of it, and then we find the area under that. And that's what we do for integrals. So how we usually write this is that we put it on the top and the bottom of the s. Well, on the side of it. So we have the integral. And let's say we want to go from 0 to 5, right? You put the 0 on the bottom, and you put the 5 on top. And that's all it means. It doesn't mean it goes from 0 to 1 to 2 to 3 to 4 to 5. It goes from all the numbers between 0 to 5. So the way to do this in math is basically what I introduced in the first couple of minutes in this video, which would be we went from x squared to 2x, right? That's the idea of derivatives, go from the original to the derivative. the concept of integrals is basically going from the 2x to x squared. So we have to make this 2x plus 5 to x squared plus something, right? So basically, what would be a function that if you take the derivative of it, you get 2x. So we can split this up into parts. We could do it to 2x and then do it to 5. So usually derivative integrals have the same properties as derivatives. So if you're adding, subtracting, it kind of just follows these basic rules. If you're multiplying, then basically you could just move the 2 outside. So if you have like the integral of 2x, then basically you're gonna write the same thing as 2 times the integral of x, right? Or if you have the integral of like 2 plus 5, you could say that as the integral of 2 plus the integral of 5, right? Or you have like that's just constant. So if you do the integral of f of x plus g of x, you could say the same thing as the integral of f of x plus the integral of g of x. So you can split this up into parts. If you're adding or subtracting, or you're just doing some kind of like scaling, then basically you could do that. But if you have something like the integral of f of x times the integral of g of x, you cannot change this into the integral of f times the integral of g. It doesn't work. It only works for plus and minus. We'll be covering the ideas of how to do this in the next video where we talk about the rules for integrals. So for now, we're just going to show the example. So we have 2x plus 5 dx from 0 to 5, right? So this thing was our derivative, okay? So this equation is our derivative. We want to find our original function. So what we do is basically we're going to take the integral of that. So what you got to think about, since if you remember the power rule for derivatives, what we do is that we take the like a to x, right? We have to write that into a x and then x minus 1. This is the power rule for derivatives, right? Well, basically, it's just got to go one less power. So if this is linear, then basically the number before is quadratic. So you have x to the powers 2. So the derivative of x squared is 2x, so you know that's correct. So let's do 5. So since this is a constant, the one before it has to be linear, right? So the linear one is x, right? The derivative of x is 1. Well, you don't want 1, you want 5, right? So you just multiply each side by 5. And it's got to be a 5x. So if you took the derivative of 5x, you just get 5, which is what you got. So that's good. So that's all we need to do. And basically, like, it's just as fast as that, basically. You just need to understand, if you do enough of these, it might be confusing now, but once you do enough of these, it kind of, like, it goes by really quick. You kind of understand of how to go from, derivative to your antiderivative, which is your integral. So basically, you can always check if this is true. X squared, the derivative of x squared is 2x. The derivative of 5x is 5, right? So you have 2x plus 5, 2x plus 5, so that's correct. But as I said before, there is always going to be some kind of constant, right? Because we have x squared and x squared plus 5, and you do the derivative of both, it's just 2x, right? You see how there's this constant that's lost? Well, basically, we're going to have to add that constant back in. So we don't know what the constant is, but for integral's sake, it kind of doesn't matter. So what we do is that we just write a c. So this is the general form for an integral. And to finish the rest of it, we're going to put these brackets. Okay. And then there's usually two ways to write it. You could write the 5 here and then the 0 here. Or you could write the 5 here and the 0 here. It doesn't matter where you put it. Usually I like to put the 5 here and the 0 here. Because if you put it at the end, you kind of sometimes forget. So you put it in front, you kind of like don't forget because you're reading from like left to right, right? So then when you see these numbers, you know you have to do the integral. But sometimes when you read it from like because if you put the 5 and 0 in the end, you sometimes like forget to look at it. It's usually just personal preference. So what I like to write is that I put the 5 and the 0 here. And then how to do the integral is basically you just plug the numbers in. So we're going to have 5 squared plus 5 times 5 plus c. Okay? So that would be your first one. Minus, and then you have 0, 0 squared, plus 5 times 0 plus c. right? You always do the top number first and then the bottom number. It doesn't matter if the top number is not greater. So if this is 2 and 3, you have to switch this 5 out to a 2, right? And this 5 with 2 is a 2. This would become a 3 and this would become a 3, right? Because you had to put it in the this is always the order. It's always the top one first and then the bottom. And then basically do the math. So this is 25 plus 25, that's 50 plus C minus 0 squared plus 5 times 0, that's 0, and then plus C. So this is why I said the C doesn't matter because they're going to cancel each other out. So 50 plus C minus 0 plus C is just 50, right? So the area under the graph, the area under 2x plus 5 from 0 to 5 is 50. So what this looks like is that you have a graph. You have, right, 2x plus 5, and then you have from 0 to 5. This area is equal to 50. And that's basically what it means. So that basically covers everything for the introduction to integrals. Thanks for watching, and I'll see you at the next math record.